This is our fourth lecture in electromagnetics, fourth module. In the first two, three lectures, we discussed about conductors, its classification and polarization. Now let us get into the continuity equation of current and what is meant by relaxation time constant. These are the two concepts we are going to engage in this lecture. Okay, so so now let us derive the continuity equation of current. It is based on the principle of conservation of charge. Let us see how it is related to the conservation of charge. For that, first we have to consider that some current is flowing through a conductor, and let me say this is the place from where your current is coming out. Okay, this is the source part from where your current is coming out. So current is coming out like that, so that it will have a current density J, and when I say current is coming out, coming out from here, as per the conservation of charge, it is like I am taking out some charge from this side and putting it out, right, in the form of current. So whenever current is coming out through this surface, whenever current is coming out, then it means that there will be a decrease in the amount of charge in this source part. So that is the basic concept. So one argument I have is that the rate of decrease of charge within a given volume with time. When I say current is coming out, coming out from a particular volume, as I have seen it here, it is this volume here. In that volume, your charge will start decreasing with respect to time whenever current is going out. Then only conservation of charge is getting an agreement, right? So because of that, your charge will decrease in this section, and similarly you will have a net outward current flow through the surface. So that is our basic concept, and that is how we are relating it with the conservation of charge. Like if I say this is a bucket of water and I am taking out water to another bucket, so whenever I am taking out water, definitely there will be a decrease in the water content in the first bucket, right? Similarly, when we say current and we are taking out the charge, so with respect to time, you will have a decrement in charge in the source part in the particular volume. So that is the basic concept. So and the current whatever current is flowing out, that I can say is that it is the closed integral over the surface, over this particular surface from wherever it is coming out or getting inside, whatever it is. So that is that J dot ds will give you what the current output, because J is the current density and ds is the small differential area. When you integrate it, you will get the total current coming out through the whole surface, which is enclosing this particular volume, right? That will be equal to what? That will, as I already said, there is a decrease in the charge, right? So we know that the current means what? It is dq by dt, or the rate of charge flow, right? Rate of charge with respect to time. So when since we are having a decrement here, I am expressing it as what? Negative minus dq in. In means what? From wherever your charge is taken. So that minus dq in divided by dt. So the current flowing out will be equal to what? The negative the negative of what? The rate of charge decrement in that particular volume. So this is our basic equation. Our current output will be equal to minus dq in divided by dt. So if we apply the divergence theorem here, since we are considering a closed surface S, we can apply divergence theorem, right? So what is divergence theorem? It can convert the surface integral over a closed surface to volume integral over volume integral into a volume integral, right? Whichever is enclosed by the surface, the volume enclosed by the surface. So our surface is integral over what? J dot ds. When we apply divergence theorem, it will become what? Del dot j dv, right? I put del dot j only here. It is del dot j dv. Okay. So that will that is when we apply the divergence theorem. Once we apply divergence theorem, let us rewrite it. Means as we have seen here, this minus dq in by dt, what that is what? The charge rate of decrease in charge in that particular volume. When we know, when I say this volume is having this particular volume is having volume charge density of rho v. if the volume is having volume charge density of rho v, then I can represent the total charge as what? Integral over the volume rho v dv will give me the total charge. So this q in I can write also as the integral of volume charge density over that volume. So minus dqn by dt will become minus d by dt of rho v dv. Clear? So now this d by dt, this differentiation, when I take inside this integration, it has become partial differential, dou rho v by dt. Why it has become partial differential? Partial differentiation, because in many objects, or in many volume, or in a general case, we might have the volume charge density to vary within the space. Let me say inside this volume, at one particular point I have a one volume charge density, and at another particular point I have another volume charge density. So even the volume charge density will not be a variable with respect to time. It can vary also with what? With respect to the space coordinates also. So because of that, I am considering partial differentiation of rho v with respect to time, because here we are only seeing about the time part, right? So it is partial differential with respect to time of dou rho v by dot t. So I hope this much is clear for you. Let us get into the next part. So this much is already clear, like del dot j dv will be now equal to, means this is after applying what? Divergence theorem. Our j dot ds over the closed surface, when we take out into volume integral, it will become del dot j as per divergence theorem. That will be equal to what? Minus dq by dt. We have made into which way? As the partial differentiation of volume charge density. So minus integral over volume dou rho v by dt dv. So from this it is quite clear that both are volume integral, both we have dv on two parts. It is about the same volume that we are discussing. So now from this equation we can directly get our equation that del dot j, means this part, del dot j equal to minus dou rho v by dot t. This equation here is referred to as continuity equation of current. This del dot j equal to minus dou rho v by dot t is defined as continuity equation of current. Now, why such continuity and all? Let us see. For if I am considering DC here, what will be dou rho v by dt? When I am saying DC here, your rate of change of volume and density with respect to time, it will be becoming what? It will be 0. Right, DC means always you have the same current flowing. So your dou rho v by dt will be 0. In that case, your del dot j is 0, right? When I say dou rho v by dot t is 0, then your del dot j also is 0. It means that the current density is not diverging. Or in another sense, what it is telling you? In another sense, it is telling you that we have seen about diverging and non-diverging field. If we take a particular point like this, and if we have a vector like this which is coming inside, then when I say it is not diverging, it means that whatever is coming inside, the same is going out also, right? This we discussed in the first module. No divergence means there is no divergence for the vector. So your current density of the current is just coming in and going out, right? If it was a diverging field, how it will be? Maybe it is coming like this at a point, right, and it is going out at another direction. So this is an example of what? Diverging field, right? Or that is what is meant by divergence. So here your charge is leaving a volume. So what we can say here, that when divergence is 0, it means that the total charge leaving a volume is equal to the total charge entering it, right? Whatever is coming here, that is going out, right? That is what we usually say as Kirchhoff's current law. What Kirchhoff's current law states, that whatever current is coming at a junction, that the same is leaving, right? So that is what we meant by what Kirchhoff's current law also. So continuity equation of current, continuity equation of current, from there we can even get into Kirchhoff's current law. So clear with this, our continuity equation is del dot j equal to minus dou rho v by dot t, or the divergence of current density is equal to rate of change of what? The decrease in rate of what? Volume charge density. Understood? So that is about the continuity equation of current. The equation is termed as, there can be, or another way what we can say is that there can be no accumulation of charge when current is flowing. This is not charge but charge only. So there can be no accumulation of charge when your current is flowing, right? That is why I said when whatever current is coming, the same amount of charge will be leaving also. So that proves that at some particular point current charge cannot accumulate. So that is why we call this equation as continuity equation. Now let us get to relaxation time. What is meant by relaxation time? For that, we have to consider three equations. First one is in the lecture 2 we derived Ohm's law in point form. I believe you remember Ohm's law in point form means what? Ohm's law in point form means J equal to sigma E, right? This you, I believe you remember J equal to sigma E, conductivity times the electric field intensity. So, and what is Gauss's law? Gauss's law in point form. The Gauss's law in point form states that del dot D equal to rho V, right? Divergence of electric flux density is equal to volume charge density. That is Gauss's law. Now, if we just take a, what is the electric flux density? Electric flux density and electric field density, they are related by what? How they are related? D is given by epsilon times E, right? That is how they are related. Okay, it is quite hard to write. So D equal to epsilon E, that is how they are related. So if I put it here and then I take out this epsilon to the other side, then you will get this equation, del dot E equal to rho V divided by epsilon. So that is Gauss's law, right? Del dot E equal to rho V divided by epsilon. Now what is our continuity equation? Continuity equation, we just stated that del dot J equal to minus dou rho V by dt. So there is something interesting here. So we have this del dot J here and we know what is meant by J equal to Z, how we can write it in Ohm's law in point form. So if we apply that here, means J, if we substitute with sigma E, right, sigma A, E, and if we think about just multiplying the sigma here, let us see what happens. So when I say when I in place of J, when I say sigma E, then that is the same equation, like del dot sigma E equal to minus dou rho V by dou T. Now the in between part, sigma rho V by epsilon, that comes from Gauss's law. Since this del dot E is rho V by epsilon, if I multiply sigma here, since it's a constant that can be taken inside, then that also will become what? Del dot sigma E. So similarly, in this right hand side, rho V by epsilon, there also I have to put what? One sigma extra. So this will also be equal, right? So del dot sigma E will be equal to minus dou rho V by dou T, which will be also equal to what? Sigma into rho V by epsilon. Rho V by epsilon is del dot T. So since we are just multiplying this conductivity here, so it will become sigma rho V by epsilon. Clear? So this is our equation, del dot sigma E equal to minus dou V by dou T, which is also equal to what? Sigma into rho V by epsilon. So from here, if we are equating, let us take out this part, means we are not thinking about this, then when these two are equal, we can just take it into one side, right? Like what? Dou rho V by dou T plus, if we take this part into this side, we will get dou rho V by dou T plus sigma rho V by epsilon equal to 0. Right, we are just taking this minus dou rho V by dou T to this side so that it will become positive, just addition. So dou rho V by dou T plus sigma rho V by epsilon equal to 0. So this equation, it is just a homogeneous linear ordinary differential equation, right? Rho V is here, you like dou y by dou x plus sigma dou y by dou x plus some constant into x equal to 0, right? Dou y by dou x plus some constant into y equal to 0. So that is quite equivalent to what? That is quite equal to a homogeneous linear ordinary differential equation. So you can solve it. How you can solve such an ordinary differential equation? By separating the variables and integrating. So first let us separate the variables. If we separate the variables, means if I keep dou rho V by dou T on one side and sigma rho V by epsilon on another side, or minus sigma rho V by epsilon on another side, this since here I have rho V part, I have to take the rho V to this side. So I will get dou rho V by rho V on one side, and the other side, this dou T will go to the other side. So minus sigma by epsilon into dou T, right? This you can try if you want. You have to rearrange the equation in a form so that in both sides, here what you have dou y by y, and here you have in a form like what? Dx, right? A into dx. So it is easy to integrate. That is why we are doing this part. So dou rho v by dou v equal to minus sigma by epsilon into dou t. Now it is easy to integrate. What is this is equivalent to what? D dou x divided by x. What is the integral of 1 by x? Integral of 1 by x is ln x, right? So since it is here rho v, so we will get ln of rho v, right? Log ln of rho v here, and since it is minus sigma by epsilon is a constant and we have dot t here, it will become what? Dot t here. When you integrate it, you will get what? T. So it is minus sigma t by epsilon, or minus sigma by epsilon into t, plus the constant of integration, right? Since we have the ln rho v on this side, when we want the equation for rho v, so in order to simplify it, we can take the c, or the constant of integration, as what? Ln rho v0, where this rho v0 I will consider as what? Another constant. Again, this ln rho v0 is a constant, and this ln rho v0 is the volume charge density whenever your time t equal to 0, right? That is what we do in integration, the initial volume charge density. So since I have got ln on two parts, so if I take it into this side, it will become since I have got ln on the two parts, if we take exponential of that, then we will get rho v equal to, means exponential of this one will become rho v. Rho v equal to rho v0 into e raised to minus sigma by epsilon into t. Right? When we take integrate, ln of rho v will give you what? Rho v. Ln of rho v0 will give you rho v0. Then when we take exponential of minus sigma t by epsilon, it will be the same, right? E raised to minus sigma by epsilon into t. And this since it is about exponential, this will become multiplication. So it is e raised to minus sigma by epsilon into t, right? So this is of the form what? Y equal to a e raised to minus x, right? So as an exponential function, as an exponential decaying function, because this negative is there, so we can write it as what? Rho v equal to rho v0 e raised to minus t by tr. That sigma by epsilon we are or sorry, not sigma by epsilon by sigma, we are taking it as what? Tr. Okay, this is the t. So ultimately our form of the equation is this: rho v equal to rho v0 e raised to minus t by tr. This tr here is called as relaxation time constant, or the rearrangement time. Okay, why it is so? Now let us get into this. So we have continuity equation, we have Ohm's law in point form. Basically it is about the conductor or a material in where your current is flowing, right? So if at all you have a rho v0 means what? Rho v0 is the charge density, the initial charge density at the time t equal to 0. Rho v0 is the initial charge density at t equal to 0, right? If at all, what it means, if at all in that material we are adding some charge, we are adding inside the material, we are adding some charge, that particular volume charge density is meant by rho v0. And that with respect to time, it is decaying, right? That is what is meant by this e raised to minus t by tr. Understood? With respect to time, it is decaying. So that is what is meant by t by tr, or it states that only. Whenever you are putting some charge inside the material, with respect to time, it will definitely going to decay. It will be decaying into and at infinity, this value will be what? 0. So it will become 0 after some time. So that is what our statement here is. If we introduce an initial charge inside a material, if at all we are adding some charge, it will move towards the surface, so that the volume charge density decays as per this equation, right? The volume charge density should decay as per this equation. Since this is based on what? The continuity equation of current, and based on the Ohm's law in point form. So this particular time constant, right? This will be different based on material, because this Tr means what? This Tr value is given by epsilon by sigma. Epsilon is a property of the material, and again conductivity also is what? Property of the material. So this relaxation time constant will depend on the material time. So for some materials it will be higher, and for some other material it will be lesser. So basically what it means is that this Tr means as you can see, if you apply here e raised to minus 1. So this Tr we can do like this. Let me say you have a graph like this, and your here, this is your rho v0, and from here an exponential decay will happen. So whenever your value is e raised to minus 1, that time that time from rho v0 to rho v0 into e raised to minus 1. So whatever be that value, for that what time it is taking, this time is called as what? The time constant or the relaxation time constant for a material. Its value is given by epsilon divided by, its value is given by epsilon divided by sigma. So this e raised to minus 1 means what? 30.368, or that is why we are saying 36.8 percentage of its initial value. So for the initial volume charge density to reach 36.8 percentage of its initial value, whatever time it is taking, that time is called as relaxation time constant. It will depend on the permittivity of the material as well as the conductivity of the material. That is why its formulation is what? Tr equal to epsilon divided by sigma. Clear? Now let us take two examples. If we take copper, when we have copper, the conductivity is quite high. As we know, copper is a good conductor, so it is 5.8 into 10 power 7 Siemens per meter, and your permittivity is equal to 1. For any conductor, permittivity will be equal to 1. So if we calculate the TR means what? The relaxation time. It is equal to epsilon 0. Epsilon means what? Epsilon 0, epsilon r, because it was the TR equal to epsilon divided by sigma. So epsilon again is epsilon 0 into epsilon r. So our epsilon 0 is how much? 8.85 into 10 power minus 12 farad per meter into 1. 1 here because our conductive permittivity of copper is 1, divided by the conductivity is how much? 5.8 into 10 power 7. So when we apply that, we will get the value as 1.53 into 10 power minus 19 seconds. Here we have minus 12, here you have 7. When the 7 goes up, then that minus 12 and minus 7 will add up to minus 19. Means it is so less. It is that time is very less. So inside a copper, whenever you add some charge, it will take very less time. In a very fraction of how much you can say 1 by 10 power 18th fraction of a second. By that time, your charge will get distributed that you will not even know. So the relaxation time constant is very low in copper. That is the peculiarity of conductors. Not only copper, silver, gold, or any conducting material you take, that is what is going to happen. Same thing will happen. Now let us take quartz, which is a good example for a dielectric or insulator. So in quartz, your conductivity is very low, as we know, 10 power minus 17 Siemens per meter, and your permittivity is a bit high. Your permittivity value is 5. It is 5 times the permittivity of air or vacuum. So epsilon r equal to 5, or 5 times the permittivity of copper. Now what happens? If you calculate TR, the same thing is applied here. Now here it is 10 power minus 12 and here it is 10 power minus 17. This minus 17, when it comes up, it will become plus 17, and your total time will become what? In terms of 10 power 5 seconds, right? So if you divide it by 60, you will get minutes. Again divided by 60, you will get hours. Again divided by 24 hours, you will get how many days it is. So like that, if you divide, you will get it has 51.2 days. So once you add a small amount of charge inside a quartz crystal, then it will take 51.2 days to decay to 36.8 percentage of its initial value. Means that much high. So that is what about insulators or dielectrics. So we can conclude that in conductors we have a very small relaxation time constant, and in a dielectric we have very high relaxation constant. Okay, here I have written it very badly. I am really sorry. So conductors have a small relaxation constant, and the insulators will have a what? High relaxation constant. Insulators will have what? High relaxation constant. I am very sorry about this. Okay, insulators will have high relaxation time constant. So that is about our relaxation time constant. So we discussed about continuity equation of current, and afterwards we discussed about what? Relaxation time constant. Now let us summarize. So here you first studied continuity equation of current, which is based on what? Principle of conservation of charge. That you should always remember. Principle of conservation of charge means whenever you are taking out some current through some surface, it means that inside your charge is decreasing. So that is the basis for continuity equation of current. And that same what we can correlate with what? Kirchhoff's current law. Means current entering and leaving are the same, or whatever amount of charge is leaving, the same amount is going out also, right? So that can be related. Then we also have seen relaxation time constant. It is the time it takes a charge placed in the interior of a material to drop to e power minus 1, or 36.8 percentage of its initial value. That is given by the relaxation time constant. It will be very small for conductors and it will be very high for insulators or dielectrics, right? So the TR is given by epsilon divided by sigma. So it will depend on what permittivity and conductivity of the material. So that is our summary. Now based on this you have to answer 4-5 review questions in Google Classroom. Answer that and that will be considered for your attendance. Now I am ending up the session. Next lecture will be on boundary condition, means what will happen. Till now we were discussing about one material, that we have a conductor or we have a dielectric of this permittivity and all. Now we will discuss what will happen if you have two different types of material. What will happen when we have a conductor interface, what will happen when we have a conductor dielectric interface, dielectric interface. These all things we will delve into in the next lecture. So thank you.